Okay, in the previous video, we were talking about converting numbers or writing writing binary numbers in 2's complement. And in this video, I'm going to show you how to transform or translate or convert numbers from base 10 to 2's complement and vice versa. And I showed you this example with the -9, how I started with the number 9 and then I wrote the negative of it. And then in one case, it didn't work. And in this case, it does work and so on. So let's do another example and show you how you systematically can actually calculate these values. So let's start with something very simple. Let's say I want to write the number 7. I want to now write this number in binary. Let's use 8 bits because I do want to go to numbers higher than 7 in this video. So 7 in binary is 0, 1, 1, 1, and then you add the 0, 0, 0, 0, 0, 0, 1, 1, 1. That's a 7. Now, what's the relationship between -7 and this number? Well, it's kind of the same thing between 7 and -7 base 10 with the complement in binary. What does that mean? So if I want to actually represent -7 in binary, I have to represent this number. I have to write it in a negative format. And we say it in the previous video, the equivalent negative value of a binary number is the same number, but the bits are flipped +1, right? If you remember here, we said that this value and this value are the opposite of each other. Like if this is 2, I want to subtract 2. If I want to subtract 2 from 1101, I rewrote this value by flipping the bits, right? I flipped those bits and I added 1. So I can do the same thing here. I can flip the bits and then add 1 to them. So I get 1111, 1001. This value is -7 in binary, or I'm sorry, in 2's complement. So to convert, so let's write this rule. To convert from base 10 to 2's complement, if the number, so you have two situations, right? One, the number is positive. If that's the case, you just write it in binary. Write it in binary. Sort of like what we did here. If the number is positive, we just write the number in binary. So 7 is 0, 0, 0, 0, 0, 1, 1, 1. If the number is negative, then we write the number in binary and then calculate the 2's complement. How do we calculate the 2's complement? Which is flipping the bits, flip the bits, and add 1. Let's just do that. Okay, so let's try to write the number. Let's do an example. I want to represent the number of -11 into 2's complement. First of all, can I write -11 in binary, like plain unsigned binary? No, you cannot. It has to be 2's complement. So what do I do? First step, like I said, you write 11 in binary. So what is 11? 1, 0, 1, 1. That's 11. Let's use 8 bits. So the next step is to flip the bits. 1, 1, 1, 1, 0, 1, 0, 0. Next step is to add 1. 1, 1, 1, 1, 0, 1, 0, 1. This value is -11 in 2's complement. So we start with the number, we write it in binary, we flip the bits, we add 1. Okay, so now let's convert from 2's complement into base 10. So let's say I have the following number. Actually, we can do this one, but we can do it later. Let's say I have 1101, 0101, and I want to convert this from 2's complement. This is written in 2's complement and I want to convert it to base 10. How do I do that? It's pretty easy. You follow the same steps. First, you take a look at this number. Do you think this number is positive or negative? It's negative, and I'll show you why. Because the most significant bit is 1. That indicates the bit is negative. Well, how did I actually came to this conclusion? Well, if you notice, every time we have a positive number, every time we start with a number, we write it in binary and then we flip the bits. Every time we do this for a negative number, this bit will be 1. You can try it yourself or see for yourself. If the number is positive, right? If we were supposed to write 11, we would stop. We would have stopped here. We wouldn't flip any bits. It will be 0, 0, 0, 0, 1, 0, 1, 1. But because we're calculating or writing the negative value, we had to flip the bits. So the bits will end up being at one of these bits. The most significant one should be 1, right? Those could be like if this was a different number, those bits could be like 1s, for example. You flip them, they become 0. That's fine. But this bit will have to be 1. So every time we're writing a negative number, it becomes the most significant bit will be 1. Okay, so when you're converting back from 2's complement to base 10, you take a look at the most significant digit. Is it 1 or 0? So we have two cases. If the number is, the first case, if the most significant bit is 1, then the number is negative. Therefore, calculate the 2's complement and evaluate. The other case is if the most significant bit is 0, then just evaluate the number. So in our case here, this number is 1101, 0101. We look at the first or the most significant bit. It's a 1, which means the number is negative, which means I have to calculate the 2's complement. Basically, I'm telling you, like, this number is some negative value. What is the value? Well, let me go back to the absolute value of that value. So I have to, the negative of a negative is a positive. So I'm doing the 2's complement yet once again, or in reverse order, however you want to think about it, to get the original value. So this becomes 0, 0, 1, 0, 1, 0, 1, 0. Now, am I done? No, I have to add 1 as well. So this becomes 0, 0, 1, 0, 1, 0, 1, 1. Now I evaluate. How much is this value? You can simply figure out that this is 1, this is 2, right? It's 2 to the power of 0 is 1, 2 to the power of 1 is 2. That's how I calculate it. This is 4, this is 8. So this is 8 plus 32, that's 40. 40 plus 3, that's 43. So this answer here is 43. But we started with a negative number, so this is actually negative 43. This number is negative 43. Okay, so let's do it backward. Let's see if we actually do get that number if we start with negative 43. So let's do negative 43, and we want to write this one into, actually, oh, sorry, before I do that, let's do another example where we have a positive number. So let's say I have 0, 1, 1, 0, 0, 1, 0, 1, 0. The question is, how much is this value? Well, you take a look at the most significant digit. The most significant digit in this case is 0, which means the number is positive. So I don't have to evaluate its absolute value. It already represents its like positive nature. So I don't have to take the 2's complement. I just evaluate it. And this is 74. It's a positive 74. Okay, let's do a couple of more examples. Let's do that negative 43, and I want to write this in 2's complement. So where do I start? First, I write 43 in binary. So just to be extra safe, I'm going to assume my answer was wrong. So I'm going to actually punch the number here into a quick calculator and see how much is 43. 43 turns out to be 0, 0, 1, 0, 1, 0, 1, 1, which is what we had before. Then you take the complement of this, you flip the bits, 1, 1, 0, 1, 0, 1, 0, 0. Then you add 1. This becomes 1, 1, 0, 1, 0, 1, 0, 1. Oh, it's the same number that we had here, right? They're the same number. So negative 43 is written like that. Let's do one more example. I want to convert 1, 0, 1, 0, 1, 1, 1, 1 from 2's complement to base 10. What is the rule? I look at the most significant digit. The most significant digit here is 1, which means the number is negative. So what do? I need to take the 2's complement and then evaluate. How do I take the 2's complement? I flip the bits and add 1. So flip the bits, 0, 1, 0, 1, 0, 0, 0, 0. Add 1 to them, you get 0, 1, 0, 1, 0, 0, 0, 1. And that number is 81. But again, because the most significant digit in the 2's complement was a 1, this is a negative number. So this is negative 81 in base 10. Okay. Let me give you one more example, or let me explain one more thing. Can I represent very large negative values? The answer is yes, but I need more bits. Why do I need more bits? Because the most significant bit here, as you see, it's kind of telling me the sign of the number. Indirectly, it is giving me the sign of the number, right? If it's 0, the number is positive. If it's 1, the number is negative. So I'm losing a range of values to represent. When I need to represent a large number, I will need more bits. And going back to my example with the number like representing negative 9 using 4 bits, if you remember, if we have 4 bits, like 1, 1, 1, 1, right? Or 0, 0, 0, 0 to 1, 1, 1, 1. How many values can I actually represent with 4 bits? The answer is I can represent 16 distinct values with these 4 bits. Now, that means if I'm using 4 bits to represent positive and negative values, it means that half of them will be negative, half of them will be positive. Well, if I have 16 values, that means half of them, which is 8 of them will be positive and 8 of them will be negative. So I can't represent negative 9 because I cannot represent 9 different negative values. I hope that kind of cleared up the situation why I cannot represent negative 9. I can represent 16 different values in this range using 4 bits. And if I'm doing positive and negative, I'm using them as 2's complement. So if I'm representing unsigned binary, this is a 0, and then this goes all the way up to 15. Okay, that's fine. This is unsigned binary, meaning no 2's complement, no nothing. But if I'm using 2's complement, it doesn't go from 0 to 15. Half of them will be negative and half of them will be positive. So I can't really have this range, right? So it has to be maybe you should answer what it has to be. What can I represent? I can represent 0, 1, 2, 3, 4, 5, 6, 7. Now, can I represent 8 here? No, I cannot. Why? Because the most significant bit must be 0 to represent these positive digits, right? So the biggest number I can represent as a positive value in 2's complement with 4 bits must be 0. That's the leading bit, must be 0 to make it positive, followed by 1, 1, 1, which is a 7 in this case. So these are the only positive numbers I can represent with using 4 bits in 2's complement, right? And the same thing kind of goes for the negative value. So I can only represent 8 values in the negative territory. So that's why I cannot use 4 bits to get -9. If you like, we can do this exercise quickly. What is the smallest? So we said this is the biggest positive value, and this is the smallest positive value. So it goes from 0, 0, 0 to 0, 0, 0, 1, 1, 1. Okay, that's representing 0 in decimal to 7. What's the smallest negative number? The smallest negative number is 1, 0, 0, 0, right? And the largest one is 1, 1, 1, 1. So let's do 1, 0, 0, 0. How much is that? The number is negative. So we have to flip the bits, 0, 1, 1, 1, add 1. It becomes 1, 0, 0, 0. This is -8. Oops. And then, actually, I flipped what I had to say. So this one, it's mirrored. So this one is the smallest negative number. So this is in magnitude. So this, we flipped all the bits, add 1, becomes 0, 0, 0, 1, which is equal to -1. Right? So my negative values are bordered or contained between -1 and -8. I cannot go to -9. If I want to go to -9, I will have to use an extra bit. Like that. And the same goes with larger values and so on. Hopefully you learned from this how to convert from negative or from decimal to 2's complement for both negative and positive values, as well as going from 2's complement to base 10 for negative and positive values. And I hope you learned about how big is the value that we can represent in 2's complement, the negative and the positive, and why that's the case. Thank you for watching, and I'll see you again.